finite Fourier sine transform and finite Fourier cosine transform. So let's recall the formula first, and then we'll move to the handout. So if you have a function fx which is defined on the interval this way, x is between 0 and L. Okay, so this is a finite interval, and particularly 0 to L, not minus L to plus L. Okay, so when the function is defined in this range, okay, we can define two types of transformation. First one is we call it as the finite Fourier sine transform. So finite Fourier sine transform, how it is defined? We define it as finite Fourier sine transform of the function fx. It is denoted by f bar s n equal to 0 to L f of x into sine n pi x by L. So this is Fourier sine transform. The corresponding inverse one, that is fx equal inverse is fs inverse of f bar s, which is actually equal to our original function fx, because inverse, if we take the inverse, we get the original function fx. Which is equal to this time summation, that is 2 over L summation n equal to 1 up to infinity f bar s into sine n pi x over L. Okay, so this is the first one, that is finite Fourier sine transform and its corresponding inverse formula. Okay, similarly, we can define finite Fourier cosine transform. Finite Fourier cosine transform, which is defined to be fc fx, and we denote it by f bar c n. Actually, n is an integer. Okay, we know that n is an integer. N belongs to set of numbers. Okay, so this is equal to, we know that 0 to L fx into cos n pi x over L into the inverse f inverse c of f bar c n is equal to actually our original function fx, which is equal to, you have to be careful here. The first one is 1 over L. Okay. F bar C naught. F bar C naught. That means that in this function you have to put n equals 0. Okay. Plus 2 over L summation f bar C n cos n pi x over n. So here we know that fc bar is equal to integration 0 to L. So these are the four formulas. This is the finite Fourier sine transform, and its inverse finite Fourier cosine transform and inverse. Okay, so this is what we studied in the last class, and yeah. So here you have to be note that actually the limit, the range of x should be like this, 0 to L. Okay, then only we use the finite Fourier transform, sine transform, or either sine transform or cosine transform. Okay, so otherwise we can't use this one. The range should be in this form, 0 to L form. Okay, right. Now I think I remember we did this question, and hopefully you can do these questions. And we'll do one of these questions, the first one. Find the inverse finite Fourier sine transform of this function, 1 over 2n plus 1 whole n squared into cos 2n pi, and the range is 0 to x. So we'll work out that one, example number 6. So actually we asked to find inverse finite sine of the function. Function is given 1 over 2n plus 1 squared cos 2n pi by 3. So that is 1 over 2n plus 1 all in squared into cos 2n pi by 3. So actually, this is our f bar n s. So the question is what is your fx? Means that we want to find fx. So according to the definition, this is equal to the sine transform. Therefore, we know that our range is what? X is between 0 to 1. So our L is equal to 1. In this case, our L is equal to 1. Therefore, 2 over L. No? So 2 over 1. So L is equal to 1. Therefore, 2 over 1 into summation of this one, Fs bar, F bar s n. So that is 1 over 2n plus 1 all in squared into cos 2n pi by 3 into sine, because the sine transform. So sine n pi x over L. So our L is equal to 1. So this is the inverse one. So if you write it properly, so if you want, you can do some simplification here. Otherwise, you can just keep as it is. 1 n equal 1 up to infinity. Okay, so therefore this is equal to 2 times summation of. You can't take this out of square because this is depending on n. Therefore, you can write it as 1 over 2n plus 1 squared into. If you want, you can simplify this. Otherwise, you can keep as it is, no problem. So you can say that sine. Okay, let's write first cos. So whatever it is, you can write it, no problem. Cos 2n pi by 3 into sine. So that is the answer. Okay, that's all. Very simple. That's the answer. Because here actually it's a series, no? So if you can simplify this one, and you can simplify. Otherwise, you can just keep as it is. N equal 1 up to infinity. Okay, so that is the inverse of the function. So this is our function fx. This is the inverse of this Fourier inverse finite Fourier sine. Okay, the function f bar is n. Do you understand this? Hello, do you understand? Tell me whether you understand or not. Hello. Right. Then second one. The second one, this one. Here they are asking you to prove this one. Here they are asking you to prove this one. Our L is equal to actually 1. So actually, so if you just try to do this in the previous way, okay, so you will get the series form of the expression. You will get some series form. But here they are asking you to show this one. Therefore, what you can do is better you find the Fourier sine transform of this one. Fourier sine transform of finite Fourier sine transform this function. And if you show that, the finite Fourier sine transform this function is this one, then reversely you can say that the inverse of this one is this one. Okay, because if you just find the finite Fourier sine transform this one, okay, what will happen? Let's do that also. Example number 2. So they are asking you to show. This time they are asking you to show inverse finite Fourier of 1 minus cos n pi over 1 minus n cube equal to half times x into pi minus x. So if you do in the previous way, what will happen? Here our x varies from 0 to pi, no? So that is over there. So if you use the previous way, you can say that your fx is equal to 2 over L. That means that 2 over pi 2 over pi summation 1 minus cos n pi over n cube into, sorry, we don't want to put a bracket here, into sine nx, because n pi x over L, no? So that is equal to, actually we have n pi x over our L is also pi, so pi get cancelled, so we get nx. So this is the inverse of that one. So we have directly found this one, but here actually we have a problem now. We want to actually show that half times x into pi minus x. So it is very difficult to simplify this and show this is equal to half times x minus pi minus x. Okay. So in this case, what we can do is, if you know the answer, okay, if you know the answer, better. So this is also correct, but actually here this time we want to show this one. Okay, we want to show this one. Okay. First of all, tell me whether you understood how I got this fx. Tell me whether how I got this fx. Just I have used the formula for inverse Fourier transform. What is that formula? Says 2 over L into summation f bar Sn into sine n pi x over L. So here my L is pi, so pi get cancelled, so I will get sine nx. My f bar Sn is equal to given, that is 1 minus cos n pi over n cube, and my L is equal to pi. So it's a matter of just substituting these things in this formula, and I have got this answer. But the thing is, if you do this way, it is not, it is correct. But the thing is that this time we have to show that the inverse is equal to this one. So here we are struggling to show the required form. Therefore, if you get a question like this, better what you do is you find the Fourier transform of this function, finite Fourier sine transform of this function. And if you get this one, then that is the answer, isn't it? So let's find the finite Fourier sine transform of the function x into, sorry, half times x into pi minus x. Okay, so we'll find the finite Fourier sine transform of this function. So according to the definitions, we know that this is equal to actually function x is, the range is this one, no? So this implies my L is equal to pi. Therefore, I can write it as 0 to pi, okay, 0 to pi, half times x into pi minus x into sine n pi x over pi into dx. So pi get cancelled, pi get cancelled. So I can do some simplification. I can take half out. So that becomes half times 0 to pi. So since I have to integrate, let me write it in this way. Pi x minus x squared into sine nx into dx. So this is equal to, I'm going to integrate by parts. Yesterday I told you a method how to do that easily. So first you keep this function as it is, pi x minus x squared, and integration of this function. So what is the integration of this function? It is minus cos nx over n minus derivative of this function. So derivative of this function is pi minus 2x, and integrate again integration of this one. So cos, integration of cos is sine, but there is already minus. Therefore, I will get minus sine nx. Another n will come, and with that I will get n squared. I have to continue until one term becomes 0. So plus, next term is plus. Okay, so if I differentiate this one, that is minus 2. And integration of this one, actually I have minus cos nx by n. So I will get, already minus is there. Therefore, I will get cos nx by n. So already n squared is there. I will get n cubed. So that is the thing. So this is 0 to pi. Okay, 0 to pi. Now, if I substitute x equal pi, okay, look at here. So many things are going to get cancelled. If I put x equal pi, what will happen? So just think of this term, first term. So I have to put pi and 0. So if I put pi here, pi into pi is pi squared minus pi squared. So this term going to be 0. If I put pi for x, here sine pi x is 0. Therefore, these two terms going to be 0 when I substitute pi. Only I'm going to remain with this term only. So that is equal to what? I will get minus 2. Okay, already I have half out. So when I substitute pi, I will get minus 2 cos n pi over n cube. Okay, other terms goes to 0 when I substitute pi. Okay, so this also goes to 0 as x tends to pi. This also goes to 0 as x tends to pi. Therefore, I will remain with only this term. So I got this one. So I'm substituting n equal pi, x equal pi here. Therefore, I will get minus 2 cos n pi by n cube. Minus, then I have to substitute 0. So if I substitute 0, here again it goes to 0 because x is there now. So again it goes to 0. Here sign again this also goes to 0. So again this also goes to 0 as x tends to 0. This also goes to 0 as x tends to 0. Okay. Therefore, I have a minus here. So minus into minus will become plus. When I substitute x equal 0, so cos nx becomes 1. So I will get minus 2 over n cube. Sorry, not minus 2, that plus 2, no? So minus 2. So if I take 2 out and if I simplify, equal to, so 2 to get cancelled, and this one I will get 1 over n cube 1 minus cos n. Okay, so now what I have got, the Fourier transform of finite Fourier transform of the function half times x into 5 minus x is equal to 1 minus cos n pi over. So from this one, I can say that the finite Fourier inverse of this one, 1 minus cos n pi over n cube is equal to half times x into 5 minus x. So this is how we can do that one. Now here actually if you do in this way, actually we are getting a series form. But actually here we want to show, actually this series is equal to this answer. The series is actually equal to that answer. Sometimes they may ask 1 minus cos n pi over n cube into into sine nx equal half times x into 5 minus x. You can do by both method and you can do this one. Actually here they are asking you to find only the inverse. Okay, so this is actually equal, but here since they are asking you to show this, we are doing this way. Do you understand, students? Tell me whether you understand. Speak please. Today is the last class on this. Okay, fine. The last question, I think actually you can do this one. Okay. So the function is given. Sometime I want to tell you some in some book. In some book, the finite sine of a function fx written this way. Okay. Sometimes they write fs to fsn. Simply they will write this way. Okay. So simply they will write this way. Inverse they will write like this. So they are just notations. So don't get confused with anything. Okay. All these are same thing. All these are same thing. Okay. Don't worry about that one. So here also they are asking this one. So find fx, capital Fx. If the inverse is this one. If the inverse is this one, they are asking the capital Fx. So it's just a matter of, because here we have nothing to prove anything. We have to find it. So let's do that also. So example number 3. We are given inverse of function capital Fx. So the function of the capital Fx, the function is given. What is that function we are given? 6 over 2n plus 5 6 over 6 over 2n plus 1 pi. No, sorry. Into sine n pi by 2 minus cos n pi. Sine n pi by 2 minus cos n pi. So if you use the definition, we know that fx is equal to, here the range is 0 to 4. The range is 0 to 4. So x is actually between 4 and 0. So fx, you can write it as 1 over 4. So our L is equal to 4. Our L is equal to 4. Therefore, 1 over 4 into f bar c naught plus 2 over 4. 2 over L summation this one. So that is 6 over 2n plus pi into sine n pi by 2 minus cos n pi into cos n pi x by 4. Okay, so here we are given that FCN equal to 2 pi by 2 when n equals 0. Therefore, this is 2 pi by 2. So we can substitute that value here, 2 pi by 2. 2 pi, what is that number? 2 over pi, sorry, 2 over pi. 2 over pi. So if I substitute 2 over pi, then that becomes 2 over pi, no? So 2 over pi. So 1 over 2 pi plus, and this one you can simplify, you can take 6 out and 12. So this becomes 3 into summation this one, sine n pi by 2 minus cos n pi into cos n pi x by 4 divided by 2n plus 1. Okay, 2n plus 1 into 5. So you can take 5 also out. So that is 5. So that is the answer. And if you can do some simplification here, it is better. Okay, there are so many. So we know that cos n phi equal to minus 1 to the power n. Those things we know that. Another thing is that sine. So please try this. Okay, sine n pi by 2. What is the answer of sine n pi by 2? Can anybody tell me? What is the answer of sine n pi by 2? So it is either it is minus 1 to the power n plus 1, no? N plus 1 if n is odd, and 0 if n is even. Okay, 0 if n is even. So those kind of simplification you can do here, and you can do this one. Okay. So that's all about these questions. Okay, I will send a tutorial also. There are some challenging in the tutorial. There will be some challenging questions. Okay, so please please simply try to simplify this one and get this one. Now we'll move to the last handout, which one is talking about. So let's close this one. So many tabs. So now the last handout. Actually, there are only 2 pages here. That is a finite Fourier sine and cosine transform derivatives. Now let's talk about the sine and cosine transform derivatives. Why we are particularly discussing derivative is we are going to go for the application, that is solving partial differential equation. So if you want to solve partial differential equation, then actually we need all these things. Okay, so the proof of these things are very important. There are 10 things. Okay, there are 10 things here. So out of these 10 things, the last 4, particularly the last 4 are important. Proof is important. Okay, proof is not given in this handout. Let's prove it. So proof is important. Okay, so now let's do one by one and quickly move to our thing. So first one, okay, we have a function capital Fx. Okay, it's actually a single variable function, single variable, and the range of x is this one. X is less than n. Now the first question is, what is the Fourier sine transform of fx? Finite Fourier. Here we are talking about the finite Fourier. F dash, first derivative. Can anybody tell me what is the first one? So we'll just use the definition. Okay, we'll use the definition. So definition says what? 0 to L. Okay, 0 to L. F dash x into sine n pi x over L into dx. So now we'll differentiate this one. This is equal to, okay, so using integration by parts, we can have what? F dash x okay into integration of this one. So what is that integration? Sine n pi x, sorry, not sine. So it should be cos now. So that is minus cos. Minus cos n pi x over L, okay, into L over n pi, okay, L over n pi, minus minus what? Minus integration 0 to L, okay, derivative of this one. So what is the derivative of this one? That is fx. No, sorry, derivative of this function. So derivative of this function is what? Sorry. We'll take other way. Okay, we'll take other way. I'm sorry. We'll take this as our first function and this as our second function. So that is equal to first function as it is, no problem, and integration of this function. So I'm taking this as my u and this as my v. Okay, I'm taking in that way. So first function without any problem, u, that is sine n pi x over L, and integration of f dash x. So integration of f dash x would be integration of f dash x would be fx minus 0 to L 0 to L. So actually I have to substitute the value 0 to L. Integration 0 to L and differentiation of this one. Differentiation of this one is what? N pi over L sine cos. No? Please look at carefully. Cos n pi x over L into fx into dx. Okay, so that is equal to, if I substitute x equal L, LL get cancelled, sin n pi. Sin n pi is 0. If I substitute 0, that is also 0. So this becomes 0 minus, and I am taking n pi L out. So that is n pi L integration 0 to L. Okay, I'm writing the fx first. Cos n pi x over L into. Okay, so this is equal to minus n pi L into, what is this? Can anybody tell me what is this? Can anybody tell me what is this? Look at the thing. Fx into cos n pi x over L. What is that? This is nothing. Yeah, Fourier cosine. So that is finite Fourier cosine transform of fx. Okay, finite Fourier cosine transform of fx. You can write it in this way, or you can write it as minus n pi L into capital F bar S N. Okay, so that is why the first one, look at here, minus n pi over L FC fx. Do you understand this one? Tell me whether you understand this. The proof is not given, so you have to do that. Right. The second one, similarly, you can do for the cos. Similarly, you can do for the cos. So these four are not important. So because not important in the sense that actually here in this course we are going to discuss solving partial differential equation. Therefore, we will be concerned on two variable cases. Okay, but you must know the proof of these also. Proof is necessary. Okay, but look at very simple. The similar way you can do this one. Okay, always you take f as your v, f dash as your v function and sine as your u function. Okay, so let me do this one. Second derivative. Yes, so you have to try this one. Nah? This one is homework. Similar way, no any problem. This is also homework. Okay, so I will write this one, second one. So fc dash is equal to this one. Let's try this one. So second one. So we want to find out Fourier cosine, no? Fourier cosine of f double dash x. So according to the definition, so I'm going to use the thing. So that is 0 to L f double dash x into cos n pi x over L into. So since it's a second order derivative, I will do the same thing for two. I will do the same thing twice. So let me take this as my v function and this is my u function. So this is equal to, so u function I will write as it is, cos n pi x over L into integration of this function. So what is the integration of second derivative? That is the first derivative. So I want to substitute the value 0 to L minus, okay, again what? The derivative of this function. So derivative of this function, that is so integration 0 to L. The derivative of this one is, we know that minus. So let me write the constant first. So n pi L minus is there, sine n pi x over L into f dash x to dx. Okay. So if I substitute L equals 0 here, if I substitute L equal, sorry, if I substitute x equal L, I will get cos n pi, and this one is, so if I simplify the first part, if I substitute x equal L, this become cos n pi. So cos n pi is actually, we know that minus 1 to the power n, minus 1 to the power n f dash L minus, if I substitute x equals 0, this becomes 1. This is f dash 0. Okay, minus. So minus into minus, this becomes plus. Let me take n pi L out. N pi L out. Let me write it in the plus. So n pi over L out. N pi L out, and then again I'm going to do the same thing. Sine n pi x over L. So I'm going to take this as my d, and this as my u. Okay. So then that will become sine n pi sine n pi x over L into integration of this one. So integration of first derivative is fx. Fx. So here I want to substitute 0 to L minus integration 0 to L derivative of this one. So derivative of that one is, we know that n pi over L cos n pi x over L, and the integrate that is fx. So this is equal to, so already I have this term, that is minus 1 to the power n f dash L minus f dash 0. And if you substitute like earlier, if you substitute x equal L, this term vanishes. If you substitute x equals 0 also, this term vanishes, isn't it? So I have n pi L, here also I have n pi L. So minus, I have n pi L, and this becomes 0 minus, I'm taking this n pi L out. And if you look at this one, this is what? This is nothing. Fourier, actually you can write it, Fourier cosine transform of capital Fx. Okay, so if you simplify this, minus into minus, that become plus, n squared pi squared L squared. So I'm writing this one first. So that becomes n squared pi squared L squared into Fourier, finite Fourier cosine transform of capital Fx minus this one. So, okay, minus 1 to the power n. So that is plus can write it minus 1 to the power n f dash L minus f dash. So that is the answer. So let's see whether it's correct. Look at here. Yeah. So n squared minus is there. No? There's a minus. I don't know why we are getting minus here. So anybody got this? Why we are getting minus here? What is the reason we are getting minus here? Any reason why we are getting minus here? There is a minus coming. No? So how is that the minus? So where I have made a mistake. Plus y. There should be minus, I think. I don't know why. Where I have made a mistake, there's a minus problem. Where's the minus? Where is that? Minus into minus, minus into minus is plus. Have you found the mistake? Hello? Anyway, I have made a mistake, so it is okay. And integration of this one, integration of cos, differentiation of cos is, that is fine, minus, and then here it is okay, and here it is sine pi x into integration of this function. So integration of sorry, not the differentiation of sine. No, differentiation of sine is actually cos, no problem with that. And then this is okay, and this one, what's the problem with this one? Differentiation of cos. Differentiation of where this minus is coming from? Any idea where this minus is coming from? Yeah, that minus is coming from here, no? That is minus in 5. Have you got? Have you found my mistake? I have made a small mistake, I think. So anyway, you check this one. There is a minus here. I just check this one. Okay, everything is same. Everything is same. Okay. Now let's talk about this one. This is the most important part. Okay. So here we have two variable cases. Now we have the function u equal ux comma t. Okay, the range of x, because we are going to take the Fourier transform with respect to x. So this is the our main variable. Okay, this is the secondary variable. Either it can be y or anything. So here the range of x should be 0 and 10 in order to do the Fourier transform. Okay, now let's talk about the Fourier sine transform of the first derivative of this one. Da by u over da by x. Okay, u is a function of two variable x and t. The range of x is 0 to l. So what is the finite Fourier sine transform of this function? So according to the definition, this is equal to 0 to l da by u over da by x into sine n pi x over l into dx. Okay, so let me take like earlier, let me take this as my v function, this as my u function. Okay, so this is equal to, sorry, this is equal to So what I have to do, I just write my u function as it is. So that is sine n pi x over L, sine n pi x over L into integration of b function. So what is the integration of this one with respect to x? That is nothing but u. U, I have x comma t, x comma t, and I have to substitute what 0 to L minus 0 to L and this function. So differentiation of this function. So differentiation of this function is, I know that n pi over L cos n pi x over L into, and integration of this one is, I know that u into dx. So if I substitute x equal L, this becomes 0. X equals 0 also, this becomes 0. So this becomes 0 minus, and if I take n pi L out, and can anybody tell me what is this n pi L out? 0 to L, I have u x comma t into cos n pi x over L into dx. So can anybody tell me what is this? So this is equal to n pi over L into what is this? Tell me quickly. We are running out of time again. What is this? Yeah, that is Fourier cosine transform, finite Fourier cosine transform. So finite Fourier cosine transform, how do we write this one? So you can write it as u bar. Actually, our variable is n. In the place of x, we have to put n. Like earlier, we put omega. This time we are putting n because finite, no. So finite means we put u bar. You can put n comma. Okay, so that is what here. That is what you can see here. Minus n pi L over Fourier transform of u. Fourier transform of u. Okay, you understand this. Similarly, we'll talk about a second derivative. Now this is Fourier sine transform of x. Fourier sine transform of first derivative. So if you talk about the Fourier cosine transform of first derivative, Fourier cosine transform of first derivative, that is also same, 0 to L da bar u over da bar t cos n pi x over L into. So that is equal to, again, like I'm going to take this as my v function, this as my u function. So this is actually, I know that first function as it is, cos n pi x over L into derivative or integration of this function, that is u x comma t, and I have to substitute the value 0 to L. Here you don't need to put n because we are differentiating. So this is actually x. X minus integration 0 to L, and differentiation of this one, we know that okay, differentiation, I will first try the integration u into differentiation of this one, we know that n pi L, so I am taking n pi L out, anyway I write it n pi minus n pi L into sine n pi x over L into just dot. So this is equal to, now if I substitute x equal L, here this becomes minus 1 to the power n, because x LL get cancelled. So we will get minus 1 to the power n u. X in the place of x, you have to substitute L. So L comma T minus, if I substitute x equals 0, this becomes 1. So we get here u 0 comma T. Okay. Minus, so there's a minus out. I'm taking this n pi LO out, so that becomes plus n pi LO out, 0 to L u into sine n pi x over L into dx. So this is nothing but the sine transform. Therefore, I can write it as n pi over L u bar sine transform n comma t, okay, plus minus 1 to the power n u L comma t minus u 0 comma t. That is the first derivative. You can see here. So order is different, but that is the one. Do you understand this? How we got this one? Hello? Do you understand? Tell me whether you understood or not. So this one you have to do it as a homework. I will do this one. Second derivative. So now let's talk about the second derivative. Fourier sine of da bar squared u over da bar x squared. Look at the variable. We are differentiating with respect to x, equal to 0 to L da bar squared u over da bar x squared into sine n pi x over L into. So that is equal to, so similarly I'm going to take this as my v function, this as my u function. So first function is like earlier, sine n pi x over L into derivative integration of this function. So this is actually first derivative, sorry, second derivative. Therefore, we'll get the first derivative, that is da bar u over da bar x. Zero to L minus integration 0 to L sine n pi x over L into, okay, I'll write da bar first, and that is easy for us. That is da bar u over da bar x into sine, not the sine, differentiation. No? So differentiation of this one is cos n phi. So I take n phi L out. Now you are familiar with why I am taking n phi L out. And here I will get cos n pi x by L. Okay. So if I substitute x equal L here, that becomes 0, because sine n pi is 0. If I substitute x equal also 0. So this is equal to 0 minus n pi over L. And what is this? Can anybody tell me what is this? So I'm just again you can do this one. What is this actually? This is Fourier cosine transform of first derivative. We have just got the answer. Fourier cosine, that one, no? Fourier cosine transform of first derivative. What is that? N pi L u bar NST. So I'm just going to put that one. So minus N pi L N pi L over what is that? U bar NST. That is U bar NST. So U bar NST minus what is that? Minus 1 to the power UL comma T minus or plus. Yeah, plus, no? So plus U what is that? U sorry, minus 1 to the power, no? Minus U 0 comma. So if you simplify this is minus is here. So this one is minus. So I'm correct, no? This is minus, no? Okay, anyway, I'll check that. Yeah, that is we are getting the answer, no? So that is equal to, if I multiply this one, you will get minus n square pi square L u bar S n comma T minus n pi L minus 1 to the power n 2L comma T minus U. Do you understand? There is a minus, no? Please check these. There are small mistake in minus and plus. That is here. First derivative we are getting minus here, no? We are getting minus for this one. Yeah, we are getting minus for this one. Then we have to put plus here. If I put plus, it is correct, no? Sorry. So you have to multiply by minus n pi L, no? So we have to multiply by minus n pi L. Therefore, if I want to multiply by minus n pi L, then sorry, this should be plus. I'm sorry. You check this one, okay? You check this one, please. Check this one. I'm sorry. Okay, please check these two, but this one is correct almost. I think this one is minus because we are multiplying by minus n pi L now. So when you multiply by minus n pi L, this will be there. So I think there should be plus here. Please check this. Okay, please check this also. Okay. So do you understand this? How to get these things? Hello, do you understand how to get these things? Tell me quickly. Do you understand how to get this? What about others? Only 277. Only few are responding. 72, 4. What about others? Do you understand? Hello. Tell me whether you understood or not. Right, fine. Now we know this one. So now I am asking a simple question. What is Fourier sine transform of what is Fourier sine transform of da by u over da by y? What is Fourier sine transform da by u over da by y? This is equal to integration 0 to L da by u over da by y into sine n pi x by L into dx. But here it is with respect to y, no? Therefore, using the Leibniz theorem, what you can do is you can take this out. D over dy and integration 0 to L u into sine n pi x over L into. Therefore, this is nothing but d u bar n comma t over d. Okay, so if it is with respect to the second variable, actually that will come in this form. Say for an example, if you want Fourier cosine transform of da bar squared u over da bar y squared. So this is nothing but, sorry, I want to put a s here, sorry. So this is nothing but e squared uc nt. Sorry, I'm sorry. Here my variable should be t, no? I'm sorry. Here also it should be t. My second variable is t here, no? Sorry. I'm sorry. So if it is with respect to t, then this is u bar c n comma t over t. So if it is with respect to the second variable, then it is this way. If it is with respect to x only, you have to do this one. Okay. I think there are some small mistakes here, plus minus mistakes here, but this one is correct. This one is correct. This one also we got the answer. This one is also correct. No problem. This one is also we got the answer. I want you to check these three things and these two things. Okay. Please check this one. Okay. Now we'll come to the last part. That is solving partial differential equation. Now, if you look at this formula, okay. Now we look at here. This is a very important thing. If you use the sine, if you use the sine transform, what are the things you need actually when you have to do the Fourier sine transform? What are the things you need? You need u0 comma t and ul comma t. You need this one. If you are using the cosine transform, you need this one. So if you actually work out on this, you will get this formula. So here actually you want the first derivative of u with respect to s at L comma t and first derivative of u with respect to x at 0 comma t. You need these two things. So based on these two things, you can decide. If you know u0 comma t and ul comma t, if you know ul comma t and u0 comma t, then use the Fourier sine transform, because in this formula actually we know we need these things. If you know da by u over da by x at L comma t and da by u over da by x at 0 comma t are known, then you go for Fourier cosine transform. Okay, so based on the initial conditions, actually we will decide what transformation we should go for. Okay, if you know u0 comma t and ul comma t, you go for sine transform. And if you know the da by u over da by x L comma t and da by u over da by x 0 comma t, then you go for Fourier cosine transform. Now this is one of the partial differential equation, and here we are given this way. Find the temperature. We'll solve these two problems. Problem number 1. Find the temperature ux comma t. Particularly now when we will use the Fourier, finite Fourier. So this is the important thing you have to think now. First thing, okay, if the range of x is, sorry, this is the important thing you should note it. Okay, if the range is minus infinity to x less than plus infinity, then you have to go for Fourier complex transform. Okay, 0 less than x less than plus infinity, and if you know u 0 comma t, then go for Fourier sine. And if you know da by u over da by x, when x equals 0, you go for Fourier cosine. So this is actually infinite case. These three are infinite cases. Now we have two things. Now our range of x is less than L. Then you have to go for finite Fourier. We go for finite Fourier. In this one, if you know u L comma t and u 0 comma t, then we go for finite Fourier sine transform. Second thing, if you know da by u over da by x at L comma t and da by u over da by x at 0 comma t, then you go for finite Fourier cosine transform. Okay, so there are 5 things. If the range is minus infinity to plus infinity, you have to go for Fourier complex transform. The range is 0 to plus infinity, and if you know u 0 comma t, then you go for Fourier sine transform. And the range is 0 to infinity, and if you know da by u over da by x, then you go for Fourier cosine transform. Here, the range is finite, 0 to L case, then you have two choices. One is finite Fourier sine transform. The second one is finite Fourier cosine transform. If you know u L comma t and u 0 comma t, then you go for finite Fourier sine transform. And if you know these two things, then you go for this one. Okay, now we'll try the problem. The second problem actually you have to work out. The answers are not given. I will give the answer for the first one. You have to do the second one, and you can, once you do this, you can send the answer to me if you wish. I can see whether it is correct or not. Okay, now let's talk about the problem number 1. Find the temperature ux comma t at any time x at any time t in a solid bounded by the plans x equals 0 and x equals 4, which is governed by the differential equation, partial differential equation, this one. Okay, so the range is given. The range of x is given as 0 and 4. Da by u over da by t equal to da bar squared u over da by x squared. Okay, so we want to find, the question is, we have to find the unknown function ux comma y. We have to find the unknown function ux comma y. So that is the question. So let's work out this one. So we have the range of x is 4x less than 0. The partial differential equation we are given is da by u over da by t equal what is that, da bar squared u over da by x squared. And we are given, in addition to that, we are given temperature at the endpoints are kept 0. Temperature at the endpoints are kept 0. What do you mean by this one? Temperature at the endpoints. So endpoints mean what? The plan x equals 0 and x equals 4. So we are given that the temperature u 0 comma t equal u 4 comma t kept 0. So that is equal to 0. And also we are given another initial condition. So these are called the boundary conditions. So these two are called the boundary conditions. The initial condition, here we are given, initial condition means when time equals 0, ux comma 0 equal 2x. So that is the problem. So our problem is this one. So this is the differential equation. subject to the boundary conditions u 0 comma t equal u4 comma t equals 0. The initial condition u x comma 0 equal to 2x. Okay, ux comma 0. So we want to solve this. So what you have to do? So what we do here, we have to identify our L. So this, from this one we have our L equal 4, because 0 to L, 0 to normally we should have 0 to L form. So here accordingly you can decide your L is equal to 4. So now you take the Fourier transform. So tell me which transform we want to take. Which transform we will take now? Tell me whether we have to go for finite Fourier sine transform or finite Fourier cosine transform. This time we cannot consider infinite because our range is actually 0 to 4 now. Therefore, this is a finite case. So in that finite case, we have to now two choices. One is to go for sine transform. The other one is the cosine transform. Tell me which one we want to select. Yeah, we want to select a finite Fourier sine transform because we know the initial conditions. We don't know the derivatives. We know ul comma u0 comma t and ul comma t. So we know this one. Therefore, we go for this one. So I am going to take finite Fourier cosine transform. Since solution. Since we know u0 comma t and u4 comma t, that is our L is equal to 4, we will use finite Fourier sine transform. Now take finite Fourier sine transform. Now take finite Fourier sine transform to the given PD. So our PD is given by da bar u over da bar t. So I'm taking the finite Fourier sine transform. If you understand this one, you can do the earlier also. Earlier means the infinite case also you can similar thing. We are doing the same thing. Here we are doing the finite. There we did the infinite case. Equal to finite Fourier sine transform of da bar squared u over da bar x squared. So what is this? Can anybody tell me what is this? Can anybody tell me what is this? This is what? With respect to which variable we are taking? With respect to t here. This one is with respect to t. This one is with respect to x. So what is this? So this is nothing but EU bar ET equal to, we know this one. What is this? Go back to this one. Look at here. With respect to x minus n pi squared by L squared. So your L here is 4. Therefore, I will get minus n squared pi squared over 16 into u bar, that is my thing, minus n pi L. So please check these things. Okay, I'm sorry. Minus n pi L. What is that? U0 comma t minus u L comma t. I think we got plus here, no? I'm sorry. I want to check that one anyway. You please check that one. Here it will not be affected because these two are both are 0. Therefore, we will not be having a problem here. So we know that here, look at here, u0 comma t, u4 comma t, both are 0. Therefore, this part is going to be 0. That is why I told you there will be no problem in this problem. So you have to check that one. So this implies as du bar over dt equal to, here we have minus n squared pi squared over 16. Sorry, I want to put, actually we are taking the sign transform now, so you have to put s. Okay, you have to put s. So you have to be careful with notations. You have to be careful with notations. So u bar s. So what is u bar s actually? So you have to say that u bar s is what? So we are taking Fourier transform of sine transform of u equal to u bar s. Okay, sorry. So that is what we are taking that. Okay, Fourier transform of u with respect to s. Okay, that's so that is I am putting this one. So this is actually a first order differential equation. First order differential equation, and it is in the form of variable separable. So this implies as, you can write this as du bar s over u bar s equal to minus n squared pi squared over 16 into v. So if you solve this one, actually this is equal to ln u bar. No, ln u bar is equal to minus n squared pi squared over 16t. So you can plus c constant. Say let me put c1. C1. So this is equal to e to the power. Okay, you can put u bar as u bar is equal to, and if you solve this one, is it possible to put this way, e to the power minus n squared pi squared by 16. Now here c1 is actually equal to, c is equal to e to the power c1. E to the power c1. Because when you take the e to the power, then is it okay? Is this okay? Tell me, we have only half an hour. At least today we want to finish this. That is why I'm moving a little fast. Do you understand up to now, students? Tell me whether you understand up to now. Yes or no? This is solving first order differential equation. It's a variable separable form. Do you understand this? Tell me whether you understand or not. Here, look at this. Is a first order differential equation. First order differential equation. The function u bar s. So I'm taking u bar s. U bar s is equal to this one. Do you understand this? Hello. Yes or no? Are you all there? Hello. ln u bar, yeah, that is this is now, what is the integration of this one? I'm integrating dy over y is what? Dy over what is what? This is equal to ln y. Dy over y, ln y. Integration dy. I'm actually I have having this one, and I am having the integration both sides. Solving differential equation, variable separable form. Is that okay now? What about others? Have you all understand how to solve a simple differential equation of this form? dy over y equal to a constant k into dx. What is the solution of these differential equations? dy over dx is equal to ky. What is the differential? What is the solution of this one? Is equal to y is equal to c into e to the power kx. That is the solution of this differential equation. Do you understand? Hello. What about others? For solving first order differential equation. Okay, anyway, I don't know what you all are doing. Right. So now what we have to do now, actually we want to find this c. So how to find this c? How to find this c? We want to use the initial condition. So what is the initial condition we are having? Ux comma 0 equal to 2x. Therefore, actually we have this one. The initial condition we are given is ux comma 0 equal to 2x. Actually, we can't use this one because we have the function u bar function. Therefore, what we want is, we want to find u bar x n comma 0. Because initial condition, we want to find this one. We can't use this one. So using this one, we want to find this one. So what is this? U bar s n comma 0 is equal to integration 0 to L. Okay. U x comma 0 into sine n pi x by definition. I am using the definition. So ux comma 0 is what? That is equal to 2x. So this is equal to integration 0 to L 2x sine n pi x or 4 into. So that is equal to 2 into. So I'm taking this as my first function. So x into integration of this one. So integration of this one becomes cos n pi x by 4 minus h into 4 over n pi minus differentiation of this one is 1 into, again I'm having integration of this one. So integration of this one is already minus is there. So I will get minus sine n phi x over 4 into 16 over n square pi square. I'm writing here. So this is equal to 2. I'm taking 2 out. Actually, this is the Fourier sine transform of 2x. So that is equal to first function x into integration of the second function. So integration of the second function is minus, sorry, writing by mouse is a very difficult thing. Minus cos n phi x by 4 into 4 over n pi. Okay. So I want to put 0 to L. So actually my L is 4 now. My L is 4. So I will put minus 4 minus differentiation of x is 1 and integration of this one is actually sine, but already there is a minus. Therefore, I will get minus sine n pi x by 4 into 4 n pi. So already I have 16 over n squared pi squared. So here I want to put 0 to 4. So this is equal to, so if I put x equal 4, so then there is 4 here. If I put x equal 4, there is 4 here. So here, if I put x equal 4, 4 get cancelled. This is minus. So here I have 4, here I have 4, then there is 8. 8 into this one is 32. Okay. So 32. There's a minus here. Minus n pi is minus 1 to the power n. Minus 1 to the power n. Minus 1 to the power n over n pi. N pi. And if I put 0, that is 0. And this one is actually minus 2. I'm multiplying here. But if you put x equal 4, sine n pi is 0. If I put 0, that is also 0. So I can write this as, I'm taking this minus with this one, and I can write it as 32 minus 1 to the power n plus 1 over n pi. So that is my u bar is n 0 comma 2. So I have now actually initial condition is given for ux comma 2. What I have to do, to find this c, I want to actually convert this initial condition into Fourier form. So that is what I'm doing here. So now I have got the answer. So this is actually equal to what? U bar Sn comma 02. So now I have U bar n comma t equal to c times e to the power minus what I have got, n squared pi squared by 16 minus n squared pi squared by 16 t. Now I want to find c. So here I know the value n comma 0 is equal to this one. So if I put t equals 0, I will get u bar n comma 0, which I got 32. 32 what? Minus 1 to the power n plus 1 over pi n pi, no? Equal, right hand side, if I put 0, then e to the power 0 is 1, therefore c. Therefore c equal to 32 minus 1 to the power n plus 1 over n pi. Therefore now I know my u bar s. U bar, sorry, I want to put s here, I'm sorry. Every time I'm forgetting. So my u bar s n comma t equal to, this is my c value, that is 32 minus 1 to the power n phi into e to the power minus what is that, n squared pi squared over 16. Now this is the thing. Now what we want to do, tell me now what we want to do. We have got the solution, but transform solution. So what we want to do, tell me. Now we have found u bar as n comma t. Now what we have to do? Yeah, we have to take the inverse. Good. So if you take the inverse, so that is Fourier sine inverse of u bar s, and that is equal to, you know, that u x comma t, which is equal to 2 over L, no? 2 over L. So 2 over L, my L is equal to 4, summation u bar s. So my u bar s is this one, 32 minus 1 to the power n over n pi into e to the power minus n squared pi squared t over 16 into sine, because we are using the sine transform, sine n pi x over 4. So you can do some simplification here. So you can take some terms which is independent of n. So you have to put n equal 1 up to infinity. So if you simplify this, here you can take a few terms out. So 32 you get cancelled. So that is 16 over 5 summation. Sorry, I think this is minus 1 to the power n plus 1, no? Sorry, minus 1 to the power n plus 1, I'm sorry. Look at here, 32 minus 1 to the power n plus 1. So we are having n equal 1 up to infinity. What is that? Minus 1 to the power n over n e to the power minus n pi, sorry, n squared pi squared over 16 t into sine So that is the answer. Do you understand this one, students? Do you understand this? Hello. Tell me whether you understand this or not. Hello. What about others? Actually, you have to work out. Otherwise, it will be a difficult thing. Right. So now I am asking you a question. Now the second question. So look at here. What is the transformation you have to go for? What is the transformation you have to go for? We are given this time da by u over da by x when at 0 comma t, and da by u over da by x at pi comma t. So which transformation we have to go for? Yeah, this time we have to go for Fourier cosine transform. Here we see initial condition. Here you are given a function 2x, but here it is given as fx. So you don't need to worry about that one. Here you have less work. The function is given as a arbitrary function fx. Actually, you can just have it as fx, no problem. You don't need to do the calculations. You can keep fx as it is. But here the function is specifically given as 2x. So in that case, you have to take this one. In that case, you have to take 2x and you have to work out. The function is given as fx, then it is easy. Okay, so that's end of this course. Okay, so you have to be careful now. You have to be careful where to use which one and what to use. So please try this one And if you are interested, you can send me the answer through WhatsApp and I will check it and tell you whether it is correct or not. Okay, so here is 0 to pi. Now I'm going to give a small summary of this Fourier transform. Laplace transform you all are very familiar with, and we have mostly discussed physical. Therefore, I don't think there will be a problem. So Fourier transform, we have a lot of kind of formula. Therefore, I have prepared a summary sheet, which is also again a lengthy one, but I will quickly go through this one. Okay, right. So now I will tell you that I give you a small picture and let's move. So Fourier transform. Okay, when I talk about the Fourier transform, we have two cases. One is the infinite. Second one is the finite one. So here, first one under the infinite, we studied first one integral representation. Here we are having series representation. Okay, under the integral representation, we had first one three types of integral representation. One is actually one is complete one. The other one is sine integral representation. When we use the complete one, the range is minus infinity to plus infinity. When we use the sine integral, 0 to infinity. Cosine, when we use that one, 0 to infinity. Okay, this one we can again write it as complex form. Complex. Okay, so complex one minus infinity to plus infinity. Okay, so here 0 to infinity, 0 to infinity. Here complete one means a omega cos omega x plus b omega cos omega, that form. That is the complete one. This is the complex one using the exponential function. Then we define Fourier transform. We have actually three types of Fourier transform. One is the complex transform. Then the sine transform. Then the cosine transform. Okay, so here actually we have the complete one, that is when the range is 0 comma c plus 2l. Then we have the sine series when the range is 0 comma l. Then we have cosine 0 comma l. Okay, then when you talk about the finite Fourier transform, actually we have only two. One is the sine, the other one is the cosine. So this is the total things we have studied. Okay, integral representation, actually there are 4. Series representation, actually there are 3. First one and the last one, actually they are same, but this is in the trigonometric form, this is in the complex number form. Okay, so here in order to use the complete one or complex one, the range should be minus infinity to plus infinity. In order to use the sine integral representation, 0 to infinity, 0 to infinity. Fourier transform, complex transform mean plus infinity to minus infinity to plus infinity. Here 0 to infinity. Here 0 to infinity. If it is a sine or cosine, in the infinite case, 0 to infinity. Complete or complex, minus infinity to plus infinity. Here, finite case, complete means c to c plus 2l form. Sine or cosine means 0 to l, 0 to l form. Okay, here also 0 to l, 0 to l. Okay, right. Let's go to my summary sheet. Right. So, if you can understand these things, I have put everything in a table, and if you can understand these things, that is enough. Okay, right. Let's talk about quickly and finish it. So I may have to take another 5 or 10 minutes additional. So please excuse me for that. Now, first one is the finite integral representation. This is called the actually integral theorem, Fourier integral theorem. This is called the Fourier integral theorem. sometime in the examination, we may ask you to state the Fourier integral theorem. So Fourier integral theorem, look at the range of f minus infinity to plus infinity. So in that case, we have this function fx is equal to 0 to infinity and this one. And at the point of continuity, at the point of discontinuity, actually we have to take the average of these two values, right hand and left hand limits. So we did a question also. Then odd function, even function. So if it is odd function, even function, then if you write the Fourier integral representation, actually, so these are the definition. These are the definition for odd function and even function. And if you take the Fourier integral representation of fx, when fx is odd function, actually we will have only sine term, because a omega will become 0. Okay, here also we are talking minus infinity to plus infinity. Minus infinity to plus infinity, but fx is odd function. So when you write the sine integral representation, the a omega will become 0. Similarly, if fx is an even function, here also we are taking minus infinity to plus infinity case. Okay, here what happen is b omega becomes 0. Therefore, this one we call it as the Fourier cosine integral, and this one here we call it as the Fourier sine integral. Why it is? Because function is odd function. If the function is odd function, a omega component becomes 0. If the function is an even function, then b omega component becomes 0. Therefore, if it is odd function or even function, actually the integral representation will be reduced to either sine or cosine, form. So that is why we are taking this one. Now here specifically we are talking odd or even. Now here the function is not neither odd or even, but it is defined in the range 0 to infinity. 0 to infinity, then we can define sine integral and we can define cosine integral. We can define sine integral and we can define cosine integral. Now, this condition we call it as the Dirichlet condition. These are the conditions required for the existence of Fourier transformation. So that is why I am putting it every time, satisfying the Dirichlet condition. Satisfying the Dirichlet condition. Okay, right. So if you don't understand, don't worry. But here what I am trying to say is, if the range is 0 to infinity, function need not to be either odd function or even function. Always we can write it sine integral representation and cosine integral representation. Okay, so you try to understand. Okay, if the function is odd function or even function, then actually minus infinity to plus infinity, the complete form, the full form normally reduced to sine and cosine. But the range is 0 to infinity. Any function, you can write it as a sine or you can write it as a cosine. Then we discussed Fourier integral representation. Then actually the last one is here also minus infinity to plus infinity. Minus infinity to plus infinity. The first one, this one, okay, this one actually can be written in this form. The same thing. Here we are using the trigonometric function. The trigonometric functions can be replaced and put it in this form. This is called the complex integral representation of the function. Fourier complex integral representation. Actually, this one, and this one are same. Both are same. This is actually trigonometric version, and this one is the complex version. Okay, therefore, this is also minus infinity to plus infinity. This is also minus infinity to plus infinity. Then we talk about Fourier transform of the function. So Fourier transform is defined in this way and corresponding inverse formula is given in this way. Similarly, here also minus infinity to plus infinity. Here 0 to infinity. When the range is 0 to infinity, actually we can define something called the Fourier sine transform and Fourier cosine transform. Therefore, the formula is given in this way. Okay, we don't need to discuss all these things. Already we have discussed. Then we discuss the Parseval identity. So in this Parseval identity, the bold thing, these are very important. Okay, so you don't need the proof is not necessary. Proof not necessary. But application, we did some question using this one. Can you remember? So please look at this one. This is Parseval identity is an important one. Then we discussed the Fourier transform of derivatives. Fourier transform derivative. Why we are discussing this one? Because now we are going to study the partial differential equation, solving partial differential equation. So this is actually a infinite case. In the infinite case, actually our variable is x. With this condition, u and ux, da by u over da by x tends to 0 as x tends to 0. Okay, the second derivative, you can put it in this way. The nth derivative, you can put it in this way. Okay, if it is with respect to the variable y, okay, like I said just before, okay, just before, you can just put as a normal derivative. Okay, here proof important. Actually, I gave the proof of this. Can you remember? I gave the proof of this one. Proof important. Proof important. Okay, so actually we are using this one. So here, from this one, you can identify, okay, if the range is minus infinity to plus infinity, right, now we'll come to that one. So now we have three transformations. One is Fourier complex transform. Other one is Fourier sine transform. Other one is Fourier cosine. So from the formula itself, we can understand. So if the range is minus infinity to plus infinity, the range is minus infinity to plus infinity, then we can use for Fourier complex transform. If the range is 0 to infinity, the range is 0 to infinity, and if you know u0 comma y, then we go for, because here in this formula we need this term. So if you know this function, you go for sine transform. And if you know da by u over da by x when x equals 0, then you go for Fourier cosine transform. So that is why from the formula itself we are deciding. But for these two conditions, actually our variable x should be this way. Okay, so that way. Now, if you talk about a finite Fourier transform, now the same thing we are going to talk for finite one. The finite one, instead of integral representation, we are giving a series representation. So the series representation is given in this form. At the point of continuity, we are writing. At the point of discontinuity, we have to take the average of these two. Then after that, actually look at the range. We have C to C plus 2L. If the range is minus L to L and the function is odd function, then actually an and a naught becomes 0. If the function is even function, in this range minus L to L, the bn becomes 0. Therefore, full form minus L to L, that means that C plus 2L form, C plus 2L form, that is minus L to L mean what? Minus L, comma, minus L plus 2L. So this is also in the form of C plus 2L form. C comma C plus 2L form. This is also in the form of C comma C plus 2L form. Okay. So here if the function is odd function, then a naught and an becomes 0. The function is even function, bn becomes 0, and the series will get this form. Now we are talking. I'm sorry, there's a mistake here. I'm sorry. Yeah. I think the same thing is repeated here. Yeah, this is odd function. I'm sorry, there's a mistake. Sorry. I will correct it and send it. This should be not fx. So you have to cut this one. And this one is actually 0 to L. So I just copied, so there's a mistake. Fourier sine series of fx, the range of x is 0 to L. Fourier cosine series of fx is cut it and cut this one. This is the range of x is 0 to L. Okay, the same thing, the same formula coming here, but here the condition is odd function, even function. In that case, we have to have the range minus L to plus L. Here, formula, the function is neither odd or even, any function, but the range is 0 to L. So in that case, we have the sine term only, we have the cosine term only. So here, we call it as the half range sine series and half range cosine series. Then we have only one Parseval identity. This is very important. This is very important. So I will definitely ask a question from this section. Okay, but proof is not necessary. Proof not necessary. Then we talk about the transformation. When you come to the finite, actually we have only two transformation. In infinite, we have three transformation: complex, sine, and cosine. When you come to the finite one, we have only two transformation. One is the sine transformation, and the other one is the cosine transformation. The formulas are given here. So here actually the range should be 0 to L. Here the 0 to L. The formula is given in this way. Now here the derivative, the same thing we talk for infinite case. Here we are talking for this one. So actually proof is important. Again, I did the proof now. We just did it. Proof is important. I will definitely ask one of these proof in the exam. Okay, proof is important. Please check this plus or minus. I also will check and tell you. Okay. So proof is important. So you know the idea how to do this one, right? Now, finally, solving partial differential equation. If you know UL comma T and U0 comma T, then you go for finite Fourier sine transform. If you know the derivative UL comma T, U0 comma T, then you go for cosine transform. So this is the summary. Okay, this is the summary. So if you understand this overall thing, then the Fourier transform is very simple. Okay, so I have told you everything, all the things, all the formula, everything I have put in one form. Okay, so actually one thing I have to check is this one, the derivative of this one. Finite case, I want to check this one, and I will update it. Here I have a copy and paste mistake. I will correct it, and I will share this summary also. Maybe tomorrow morning I have some work now, so tomorrow morning I will send. So this is end of your integral transform. So I will send a tutorial by tomorrow. There will be some questions. If you are interested, you can do it. Once the faculty view opens, we will have a tutorial discussion. Or if it takes a lot of time in between before the faculty opens, we can have a tutorial discussion online. Okay, so I will give some more time for you to work tutorial. And if you have any doubts, anything, anytime you can contact me. And even there, it may be example exercise on your handout, whatever it is. If you get a time to do it, and if you want to check the answer, you are always welcome. You can send it my WhatsApp, and I will check it and give you a feedback. Okay, so that's all. And I think I have tried my best to give you what is possible from my end. So I finish this course. Next week you will have real analysis. Okay. So next week onwards you will have real analysis, and hopefully I can finish the real analysis next week. So actually we have to do some tutorial things. So tutorial, actually that is your part. And if we get, I can discuss some of the questions. Okay. That's all. Now onwards, please start studying, because this integral transform is somewhat lengthier one. Okay, there are a lot of formula, a lot of things, and a lot of different notations, and so many things are there. Therefore, you have to be careful and do this. Okay, so I just give you a small work for interested people. Can you check all these 6 formula, 10 formula? There are 2, 4, and there are 6, 10 formula. There are 10 formula here. Can you all check this 10 formula and give me the send me the answers? Okay, interested people, please do it. Okay, interested people, please work out on this one and send me the correct one. The terms are correct, only the plus minus may be the problem. Okay, plus minus may be the problem. I also will check it, and if you get a time, please do it and send it to me. But the proof is important. Okay, so thank you for giving me this time, and I stop here, and I will send the link for real analysis from Monday onwards. Okay, thank you very much. I stop. I will definitely share this summary with you maybe tomorrow. Okay, once I update I will correct the mistakes. I will send it. Okay, right. Thank you very much, and I stop here. I will upload the today's recording also. With that, our Google folder is complete. That means that integral transform folder contains all the recordings, and whenever you get time, you can just go through and try to understand. Okay, right. That's all, and thank you very much. I stop now.